Welcome everybody on Zoom, welcome everybody in the lecture hall to this new week of big data. We are in the middle of Spark. I should say Apache Spark. I think we have to add Apache in front. We are going to continue what we've started with the RDDs. We looked at transformations, so then we looked at a few actions, which, as you know, trigger the whole computations. And then we will move over to data frames, which is a super cool feature that was added later in Spark. And yeah, that's pretty much the menu for today. Maybe we finish to end, and tomorrow we manage to end, and tomorrow we'll start with document stores. All right, so I have a few questions for you before we start. This is my first question to you. What is an RDD? Is it a resilient distributed data set? Is it a recoverable distributed data set? Is it a recoverable divisible data set, or is it a resilient divisible data set? Oh, what did I do? Well, you know, the majority is not always correct. Okay, well, that was an easy one. Okay, I'm not going to hold the suspense for longer. You got this one right. Resilience, because if you lose it, you can just recompute it, right? You just start all over, just like you would do from MapReduce if you ever lose it, and distribute it because it's all over the cluster, right? It can be petabytes of data spread over machines. So it's a partitioned collection of whatever meaning key value pairs, but it can also be something else than key value pairs. Here's a different one. MapReduce inside normally works with key value pairs, but the data sets are not necessarily key value pairs, and yet you can still have MapReduce process them without doing anything, right? So what's happening inside? How is the input converted to key value pairs? Do we use block IDs as a key and the blocks as a value because the data is always on HDFS? Do you hit the input with a hammer until it fits into the key value model? Is there a natural way to convert each input format into key value pairs? For example, HBase, the row ID acts as a key and the row as a value. Or do you use each file name as a key and the content as a value? Now, let's look at your answers. And we have a majority. Some people love to hit data with a hammer. When you wouldn't believe all the people that actually do that. Just look on social media, what people are doing. They take data that is just, I don't know, trees or graph, and they fit it into tables. Or the opposite, you know, they have data that is tables and that would fit nicely in a relational database, and for some obscure reason, they want to use a document store or a graph database to store that data. So, yeah, you have to be careful about that. You really need to find every time the correct model and the correct backend for the data that you have. All right, but the correct answer here is that there is a natural way to convert each input format to MapReduce. So this is why, as a user, you don't really need to worry too much about that, right? You can just pick your input format and it will just work. Okay. The file name as the key, no, that's not done automatically. You could technically, as a user, create, you know, a Spark, let's say a Spark RDD with file names, and then you have a map function that looks at the file, you know, for every input, but it's something that the users do themselves. It's not something that the system is going to do automatically for you. And the block ID, no, the block ID is the sharding level, right? A block gives you a task, as we see, but you cannot take an entire block as a value. That's just too big, right? That would be insane. So there are many key values in the same block, and we even saw that it doesn't quite fit because you might have the last key value that goes over the block and continues in another one, which is another reason why this answer is incorrect. Okay, here's another one. We introduced what is known as the first version of MapReduce, which was last week or 2 weeks ago. And I'm asking, what issues did it have that YARN solved? One, map slots and reduce slots are statically assigned, so they are often idle, which does not fully use its cluster resources. When a MapReduce split spans over 2 HDFS blocks, there is a massive drop in performance because data must be streamed from another data node over the network. There is a bottleneck on the job tracker, which has to do both scheduling and monitoring, jack of all trades, master of none. Or map slots and reduce slots are statically assigned before the job starts, which may lead to a suboptimal number of reduced slots. Multiple answers are possible. Let's start looking at your answers. And we have a majority for answer 1, answer 3, and answer 4. Is the majority correct? People are changing their minds. Last chance to change your mind. All right. So indeed, everything is correct. So the first answer is correct because you decide, what does it mean statically? So just to be clear, many of you are computer scientists, so it might be obvious, but some of you are not. So statically is the same as compile time in essence. So it's the difference between what you can do at compile time before you execute the program and what you do at runtime when the program is executed. So you can say compile time versus runtime, or you can say statically versus dynamically, which is the other way of saying it with query languages. Why do we distinguish? Well, it has to do with this decidability and halting problems and that sort of things, that it's impossible to tell at compile time many things about the execution of a program. You have to actually run it in order to know. However, there are many things that you can do, at compile time, and many useful things that you can do. For example, you can know the schema of your data at compile time, and then you can completely change the execution plan, your query plan. In some cases, you might not know the schema at compile time statically, so you have to use a more generic strategy at runtime that will just figure out what the data looks like dynamically, right? So this is the idea. This idea of compile time, runtime, by the way, is not just for query languages. It's also for Java, for many languages make this difference. All right, but what does it mean here? It means before you actually run the MapReduce, you already decide in version 1, these are the slots that do map, these are the slots that do reduce. This is at compile time before you run. Okay, that's answer 1. And that's not good because part of the cluster is idle. The second one is incorrect. Well, it's correct that it spans over multiple blocks, but it's not going to be something that completely that creates huge problems, right? It's something that you can deal with because that's a random access. So this is actually okay. That's not that wouldn't be called an issue. The third one is also correct because the job tracker has to do too many things, scheduling, monitoring, and in YARN, you split it. The scheduling is still done by the coordinator node, which is called, what's the name of the coordinator node in YARN? Resource manager, exactly. And the monitoring is delegated to the application master, which is running on one of the worker nodes in a container. All right, and the fourth one is Another consequence of the static assignment of the slots is that you can have a suboptimal number of reduced slots because you cannot not adapt dynamically. All right. So, do I have another question? Oh, yes, I do. Yes. Oh, this is something we'll see a bit later, but I still wanted for you to think about that now, and I'll come back to it in a special lecture about large scales. What if you have an absolutely huge data set, huge job with thousands of nodes over your cluster, and you execute it? So now you know how that works with the slots, the tasks, and so on, right? You have all the slots that are running in parallel, and then they take the tasks one by one, like the postcards that I showed you last time. However, at very large scales, there is something that actually starts happening, and many people actually only discover that when they start working for Google or Amazon because they rarely see these scales before. So try to figure it out. First possibility, the overall execution times of the job start to be unpredictable. You cannot know in advance, and that leads to massive discrepancies and unpredictability of the results and of the latencies. Or the execution becomes much smoother, uniformly distributed across machines, more predictable, thanks to micro-partitioning techniques. And this is supported formally by the central limit theorem, which I assume you all know from the probabilities lectures. Third, a few nodes will keep taking significantly more time than average to complete the execution of their tasks, and this is called tail latency. Or maybe nothing happens. Everything was suchly designed, the architecture, that everything scales up and out smoothly. And this is a hint to Star Trek for those who know. All right, let's look at the answers now. Aha, we have a majority, and the majority is correct. Indeed, this is what happens. What happens, imagine that you have 1,000 slots. You have a lot of things happening on the cluster that are beyond your control. There's garbage collection, there might be daemons running in the background, you can have something that suddenly, like the memory is swapping on the machine and so on. What happens if you're only using 3 or 5 machines is that might actually happen rarely. You actually see on your laptop, sometimes it happens, the computer just hangs, right? But if you have 1,000 nodes, it will happen on one of them. The probability is actually very high. So you can no longer ignore that. If it's guaranteed to happen at every job, then you have to deal with the fact that inevitably you're going to run your job, and then 999 of the slots are going to complete, and one of the slots is just hanging. And you're just waiting forever. The entire cluster is waiting forever for that one slot to finish. And we'll see that there are techniques to deal with that. Sadly, the technique is not to write better code. That actually doesn't work. A lot of people think they can just improve the code and it will fix the issue, but absolutely not. And we'll see in a few weeks how you can actually fix these things. And this is called indeed tail latency. Okay. So now I'm going to switch back to the slides and we'll continue. So here we are in the processing part, and we have discovered the notion of RDD in Spark, which is a big collection of whatever. I'll start calling these whatever items, which is a generic name for whatever. It sounds fancier than whatever item. So it's a big collection of items that is partitioned all over the cluster. This is a concrete example of what you can do. You can actually run a shell. It's very easy to do, even on your laptop. It actually works. You can run PySpark and you can start writing things. So in that case, the first line is a creation. We create a data set. So in that case, we parallelize something in memory. In practice, the creation would rather be reading from HDFS or from S3, creating the RDD from the data. The second line is a transformation. Here it's a flat map that converts the RDD to another RDD. And the third line is an action that is actually triggering the whole thing on the cluster. And then the computation starts happening. And then you have this table on the right that magically prints on your computer screen because it was small enough for this to work. All right? For whom is that clear? Right? So of course, in reality, it's going to be more complex than that, right? It's not just going to be 3 lines. You will have to work a bit more, but you have a restaurant menu of transformations and actions and creation functions to pick from. I didn't spend much time on the creation functions because it's really boring, right? It's just about opening Parquet, opening a text file. We'll see Parquet later. Opening a text file or parallelizing. Okay, so I left you with the transformations where we stopped, and I think the next step was to look at actions. So let's start looking at actions. So one action that you can do is collect data. What does that mean? Well, technically, logically, it's the identity function. You just have a collection of items, you return the same collection of items. It's the identity function. But actually, physically, that's not quite the identity function. What's happening actually is that all of that RDD that is spread all over machines is going to be downloaded all the way to your client and put in some local Python list, right? So now you have your local Python list that contains all of your items. Can be integers, can be objects, can be strings, and so on. So now you are going to tell me, but wait, everything is partitioned over a cluster with petabytes of data, and now we are downloading petabytes of data. Of course, that doesn't work. If you want to use collect, you need to be very careful. You should only use it if you know for sure that the size of your RDD actually can be downloaded and fits. For example, if the RDD is just a few megabytes or a few kilobytes, then you can go ahead, right? So of course, this requires some understanding of what you're actually doing with the cluster. So if you know that you have terabytes of data in your RDD, it's probably not a good idea to collect it as a Python list. I don't think many people have a terabyte of memory on their machine, even though that exists. You can, but it's not very common. Okay. Here's another action that's less dangerous, which is just a count. So this is just counting the number of items that you have in your collection, and it's an action, it's a local result, it's a local integer that you have in Python or whatever language you're using, and it tells you how many these are. As you can imagine, of course, the execution is distributed in the sense that Spark is going to count in every partition the number of items, and then it's going to add all of these counts, right, which can be done locally. Okay, so this is counts. Then we have a few others. It's not going to be a comprehensive list, right? But another thing you can do is count by value, meaning that you group the values together that are equal, and then you count them. For example, there can be 12 blue squares, 4 orange squares, and 6 green squares in that case. And this is something you get locally. These two can be dangerous. Imagine you have a collection with petabytes of data and all the values are unique. Then imagine the quantity of data that's going to reach your laptop, right? So be careful. You should really do that if you know that it might be a very large data set, but the number of distinct values is small enough that this is a small map. So this would be a Python dict, basically, mapping the values to int. Okay. Okay. So now what do we do if we cannot use collect? Yes, there is a question. Go ahead. Oh, what's going on here? Let me check the volume. Oh, now it works.
I had a question related to collect in general or count by value and such. I suppose in that case, the data type is probably the same, right? For the things that in this case, it will be integers because we just count. Couldn't we maybe make use of some very strong compression algorithms to actually help with storing that data or getting that data to a single machine in the end? Because the data type is the same, I guess compression algorithms might be better. Does Spark allow that?
Yes, it does. These are the data frames, probably that you mean. And we are going to cover them in probably half an hour, an hour. So this is coming. You're absolutely correct that since in an RDD, all the data might have the same types, then you can compress. However, the reason why it's not that obvious is that generally, if you use Java, for example, or probably the same in Python, I know more Java. In Java, it's RDD, it's using these generic templates, right? So it's RDD, and then in these angle brackets, you have a type, which is a class in Java. But you know that in a language like Java, you have polymorphism, right? So you have a class, but you might have subclasses and so on. So saying that just because it's the same type, you can compress and store efficiently is not that obvious, right? However, you're absolutely correct that in some cases, and in fact, in many cases, it is actually homogeneous enough that you can optimize, right? So these are the data frames. I'll come back to that. Actually, you already heard data frames in data modeling, right? With validation, because it has to do with that, exactly. But that's very good thinking. Indeed, you can optimize. Yeah. Okay. All right. So what if we have a billion, no, let's say a trillion, because I really don't want it to fit on any laptop. So let's say we have a trillion values in there we cannot collect. That's okay, because we can just, let's say, take the first 4 items. So here, this is the action called take, which takes a parameter. It's a number. It's the number of items that you want. If you want to compare it to SQL, that would be the limit keyword, right? You just only consider the first n values that there are, right? So this is the take function, and it returns, again, it's a local list in Python or in Java that contains the items that you want, and with the appropriate type. It's again all with generic templates, right? So if you had an RDD of integers, then you get a list of integers. Okay. So the other one is called top. It's the opposite. It takes the last ones, right? So in that case, we get the last 4 of the RDD, right? So these are just symmetric with each other. Sadly, there is no way to simulate offset. Remember offset in SQL? It's how you can also grab in, grab some items in the middle. That doesn't exist. You can still do it, but it requires a transformation that I haven't told you about. That's called zip with index. Zip with index is basically going to add increasing integers associated with the values. And based on that, you can use zip with index followed by a filter transformation, checking for the interval of the index, and then you project back to the value. For whom is that natural? Okay, very good. So it's not out of, off the shelf in Spark. It requires more effort, but you can, if you want, take specific values in there. Take sample is a bit similar to the transformation that samples here, except that in that case, it's also downloading this sample to your machine. So here you just pick 4 random items in your RDD. Here's another one called reduce, but be careful because there's reduce and reduce. Reduce in the sense of MapReduce is that you have key value pairs and you put together the key value pairs with the same key, and then you apply some transformation to the values to have them together. Here, it's only the value part of that, right? We really take the entire RDD and we apply some operation, for example, plus, that usually would be commutative and associative. It's better. And it's just going to say this plus this plus this plus this plus this plus this and so on. So it's basically a binary operator, and you just chain the calls left to right with this. But of course, if it's associative and commutative, you can actually do it in any way you want, and this is why it parallelizes well. And then you get a final value over there that would be, in that case, the sum. Okay, who is following? Okay, very good. Next, we have a few RDDs that are actually pair RDDs. It turns out that even though we no longer restrict ourselves to key value pairs, it can really be RDDs or whatever, RDDs of items, there is still a part of the Spark library that is dedicated to pairs. So if you have pairs, then you have more transformations and actions that are specifically designed for the pairs. For example, you might have an RDD of key value pairs. So each item in that case is a key value, and you have a transformation called key that is going to just return an RDD of the keys. So you throw away the values, and then you get the RDD of keys. The same exists for the values. So if you have an RDD of key values, then you just get the RDD of the values output, right? So this is a transformation, right? This is all in the cluster in parallel. Then you have reduce by key, and this, in fact, is going to be very similar to the MapReduce version of reduce, where you actually call this aggregation function, this reduce function, on all the key values that have the same key, right? So this is exactly like MapReduce here. So in essence, now if you want to express MapReduce and emulate MapReduce on top of Spark, what do you need? You need to restrict yourself to RDDs of key value pairs first. Second, you need to use the flat map transformation for the mapping part of MapReduce. So here it's a common mistake that you might do. It's not map, it's flat map. That would be the equivalent. And for the reduce part, it's reduced by key. And here also it's not reduced because reduce is an action. That's not the same. It's really reduced by key. So flat map and reduced by key on collections of key value pairs emulate MapReduce. So this is how you know that Apache Spark is a generalization of MapReduce. Even though, to clarify something that I was asked last week and that might not have been clear, Spark is not implemented on top of MapReduce. It's a completely different implementation. It's not even Java, it's Scala, the native language of Spark. But it uses a lot of the techniques of MapReduce, which is why you will see a lot of similarities. Okay, who understands now that Spark is a generalization of MapReduce, that it's more powerful? Okay, awesome. Okay, now we have something else called group by key, and this is where we're slowly venturing outside of the territory of SQL when we do that sort of things. Is that we still reduce in the sense that we group the key values by key, but we don't aggregate anything. We just list all the values that were associated with a given key as a list. Of course, that only works if you don't have too many values with the same key, right? You always need to understand what you are doing. But if there are enough distinct keys, then you can do that sort of things. You could view this as a special case of reduce by key, where the reduce function is a list aggregation, right? Where you merge two lists and accumulate the items, right? So you could see this as a special case of that in that way. Okay. Then we can sort, because it turns out that it's order sensitive. So you do have an order in the items that you have in your RDD. But in that case, it's very natural to sort by the key, right? So in that case, you group together. I shouldn't use the word group because that might be confusing. It's really not group. Well, how can I put myself out of that? Technically, if you sort, you group, right? You arrange, exactly. Let's say we arrange. So we sort all the key values ordered by key. So here, what did I do? I think I sorted them by wavelength periods. Meaning that I put the green first and then the blue and then the red. So it's nicely sorted by key. The reason I spontaneously said grouping is that you could also see the greens are together, the blues are together, the reds are together, right? So this you can actually consider that grouping is a special case of sorting. Like if you sort, you group, but if you group, you don't necessarily sort. But I'll come back to that. Yes?
What happens in the physical level? Do all the blue key value pairs have to go to a single machine when we sort, or what happens?
So the question now you're asking is about the implementation, right? So because here it's logical, on the logical level, it's actually sorting. What it's going to do in terms of implementation, there are different techniques, but basically you can create intervals of keys, and then you assign the keys that are in an interval to a specific task on the cluster, so a specific partition. But now you're going to tell me, how can I know in advance what the intervals are? Because if I don't know anything, I don't know the distribution of the keys. This is the reason why something is actually happening with this transformation that is unique to it. There's very few transformations like that. In the background, Spark is actually going to trigger a job and an action without telling you. It's actually going to do a preliminary analysis on the data in order to figure out the keys and the intervals, maybe by sampling over it. And once it knows, then it will create the partitions accordingly to put the values together. And it does that in such a way that you are assigned a partition, so you sort the partitions, but you don't sort yet what is within the partitions. It's like you do half of the job at compile time, right? So you create the partitions, but the sorting within each partition will be done when you actually trigger the action later that triggers this transformation, right? So this is why this one is a bit tricky, and it's nice that you ask, because again, normally when you do a chain of transformations without actions, there is nothing happening on the cluster. It's just preparing the query plan, but nothing flows. This is the exception, because if you do create a transformation with sort by key, you will see activity in the cluster. It will actually trigger some preliminary analysis to figure out where to direct the partitions. Does it help?
Yeah.
This is already physical, right? So, but it's good to try to understand what's going on physically. I'll come back to the physical level a bit later. Okay. So you see there are exceptions everywhere, right? To each rule. In particular, we might actually have some activity on the cluster for some transformations. Okay, here's another one, which is map values. So it's just a mapping from key value to key value, but in that case, it doesn't touch the keys. It only modifies the value. We have joins. So joins are basically putting together the key values on both sides that have the same key. But what's going to happen, it's pretty much similar to relational databases, right? So you have the joining key that would be right here. Then you would have all the parts that came from the left and all the parts that came from the right. And it's like a join in a relational table, because you really try to find all the matches. So if you have 2 tuples with a specific value on the left and 3 with that value on the right, you get 6 matches, right? This is how a join works. So here pretty much the same thing happens. It's just that here you don't see the attributes, because that's not a relational join. That's really just a join on the key values. You could, if you want, see it as a join on tables that have 2 columns, right? And that creates a table with 3 columns. For whom does that make sense? Okay. It's a shortcut, but this is how you could view it. All right. Then you have subtract by key, that is basically taking all the key values of the left, but it throws away all of those who have a key that is also on the right. It's like a subtract, but only on the keys. You have count by key. Beware, that was a transformation. Now it's an action. So count by key is going to tell you for each key how many key values you had. Okay. You have lookup, which is an action too, that says, please give me the value associated with that key, right? Assuming there's only one. I didn't check, but I assume that if there's multiple values associated with the same key, you get probably all of them. That's here you need to look at the specific of the function, right? So it's just a lookup. It's an action because you just get the value that you want. You can download it locally. Of course, the extreme case would be that every single key value has exactly the same key and there's a trillion of them. And then you can understand that probably then it's not a good idea to do a lookup in that case. So as always, you need to understand how your keys are, if they are distinct from each other or not distinct from each other. Okay, that's it on the restaurant menu so far. Any questions? Yes, I see a raised hand over there. Where is the catch box? There you go.
So I have a question about roughly the expected runtime of join as well as sort by key.
So the join?
Yeah, so like, I guess we're talking about petabytes of data on tens of thousands of machines. And like join are roughly n squared runtime.
It depends.
But like, so for instance, for these two, for join and for sort by key, like how long does it usually take in practice?
So there are several interesting things in there. First, the intuition of the time it takes is similar to the clicker question I asked you the other day. If you are looking at petabytes of data over thousands of machines, tens of thousands of machines, you can come back the following day. And even that might be optimistic because you even have people for whom it might take several days or even several weeks. So for example, some people do machine learning on top of these things. They actually train models and so on. And sometimes you actually have to let it go for months like that, right? So there are even cases. So it's very rare that you should not expect something interactive. Let's put it that way. You can, in some cases, get interactive if it's small enough. You're exploring a data set and Spark is helping you do that if the data is small enough. If you want something interactive, you would really need to spread the data very thin all over the cluster, right? That it's, for example, 1 terabyte of data spread over 1,000 machines. Maybe you could get that in an interactive manner. But in order to be interactive, you would still need to initialize the cluster before, right? Because the first time you actually use Spark, there's an extra time needed to initialize the cluster. And then the second, third, and so on queries are going to be faster, right? So if your data is spread very thin, that each machine has a little data, you might get closer to interactive, but really in most cases, that's going to take hours, maybe days, maybe weeks, right? That's the first thing. The second thing with the join is that in general, yes, a join is quadratic. However, in that case, maybe I wasn't precise enough, this is even an equi-join in the sense that you're testing for equality. It turns out that equi-joins don't need to be quadratic. In fact, they can be linear. This is amazing, right? Joins, linear. Yes, absolutely, because the secret is to use hashes. So you basically go over the first table, then you compute all the hashes, store it in a hash table, then you go over the second table and look up the hash table for every value. Then you get something linear. For whom does that make sense? Right? It's amazing, right? Linear time for joins, but it's still expensive because the constant can actually be quite high. So this is why the performance for a join can actually be quite good. You just need to be careful here too that it's going to be acceptable performance if, let's say, at least on one side, all the keys are unique. The problems with performance with the join start arising if you have a lot of the same keys, because then you get the Cartesian product within each key, and that can lead to a size explosion. Did I answer your question?
Yep, thanks.
Yeah, it was a very deep question. There was a lot of interesting aspects to discuss in there. Okay. And sort by key. So as you know, sort is n log n, right? So sort by key, I would assume is also similar to that. It's really a two-phase sort, a little bit like the way you do the merge sort, right? The merge sort, you merge the subparts and then you merge the list. But it's the opposite of that, because in that case you do the opposite. You first create the partitions and then sort within each partition. So it's kind of the merge sort by taken upside down, if you want to think of it, the way that sort by key is going to be implemented. Yeah. But the complexity is still n log n. You can not do better than n log n, as you all know from the complexity lectures. All right. Lookup. Yeah. Okay. So now let's get to the physical layer. Let's first check the time, because there is a break. I don't want to take it from you. We still have 8 minutes. All right. So the physical layer. Let's try to think how we execute all that. Well, we are not starting from scratch because we studied MapReduce, right? And we already know how MapReduce is actually working on the physical layer. Well, what's actually great is that it's not very different in the case of Spark in the way that things work. Let's take, for example, a transformation that maps this RDD over there to the other RDD down there. And we assume that there was an action triggered later that triggered the execution. Otherwise, nothing would happen. So we need to do that. Now, who thinks that this can be parallelized well, looking at this picture? Okay, and you're right about that. Why can it be parallelized well? It's a very specific transformation, right? Anybody? I saw raise hands in that corner. Yes, over there. Maybe you can throw the catch box.
Yeah, well, it's just a map. So every single block points to another block, so you can parallelize that pretty easily.
Exactly. That's the idea. So you see, it's very vertical. In order to compute this item right here, you only need to know this item right there. So in a way, it's very localized. It's very local. So this is the reason why you can parallelize it well. And in fact, you can parallelize like this. You can draw these virtual lines here, here, and here. This goes in some machine, this on another machine, this on another machine, this on another machine. And in fact, I added a legend at the bottom of the screen that you might see here, task 1, task 2, task 3, task 4. And yes, these are the same tasks as in MapReduce. This is exactly the idea. So you can, just like the splits in MapReduce, you split it, and every partition here corresponds to a task. It's like the signing of the postcards, right? A task is sign postcards 1 to 10. So the task here consists of calling, task 1 consists of calling the map function on these 3 items and returning these 3. Then there's 3 other tasks. Okay. So we can partition, well, it's already partitioned, the RDD is already partitioned, but if we have a transformation like that, that is localized with vertical arrows like that, then we can create these tasks in a very natural way. And by default, if this was directly taken from a data set over HDFS, we are not going to do it any differently than MapReduce. Basically, one block on HDFS is going to give you one task over here. And of course, you still have the problem of the last value, but that I already discussed, right? So for who understands that, every block in HDFS roughly gives you one task here for the first transformation. For whom is that clear? Okay. And then, of course, then you have the subsequent transformations, right? You can have as many as you want. Okay. Now, it means that you need to think at two levels. That's data independent, the logical level, the physical level. On the logical level, we have an RDD that's just a collection of whatever, collection of items, that a transformation is modifying to, not modifying, it's computing out of that another RDD, which is also a collection of whatever, right? So this is the logical layer. On the physical layer, you have multiple machines, and every machine is going to compute a partial a part of that transformation because we distribute over. Now, this is more accurate because here, this is the case where there's as many tasks as slots, right? Because these are the slots you probably recognize. These are the 4 machines are the 4 slots. In practice, remember the postcards again, you have more tasks than slots. So every slot is going to get multiple tasks, right? This is all dynamic. At first, they start with each one task, 1, 2, 3, 4, and maybe this one was finished, so it got task 5, then this one finished, it got task 6, this one finished, it got task, this is tongue twister. This one finished, it got tasks 7, and this one finished, it got task 8, and so on. So it's a coincidence that it's in that order, but basically you keep spreading. So this one finished got task 9, and this one finished got task 10, and finished again and got task 11, right? And so on. And then you're out of tasks, so you just wait until all the slots finish, right? So again, it's very important to understand, just like MapReduce, you spread the tasks dynamically until there are no more tasks left, and then the slots become idle. However, what's actually happening in Spark is that we might have multiple slots in the same container, in the same process. Again, it's the same idea as thread versus process. You might have multiple threads in the same process. So what's going to happen is that you create containers. They are called executors in Spark, but it's really a container in YARN that basically has memory and multiple cores, and every core gives you one slot, right? So you basically have one thread that sequentially takes care of tasks 1 and then task 5. Then you have another core 2, that sequentially takes care of task 2, task 6, task 9. What you need to understand is this is a thread, this is a thread, this is a thread, this is a thread. So this is all within the thread sequential, task after task, but it's happening in parallel across these threads. So what's new here is really that we group several slots in the same executor. The benefit is that they share memory. So it might be that this slot here is using very little memory and this one is using a lot of it, but that's good because it has a lot of memory available, right? For whom is that clear? All right, so you see all the concepts of MapReduce are here. There's the notion of task, there's the notion of slots, 4 slots, and the slots have memory and CPU, knowing that we can share the memory across several cores, CPU cores, and this is called an executor environment. Each executor is a process. Okay, so far so good. Now, what happens if we have a chain of transformations? So if you have a chain of transformations, it might look like this, right? You might think very naively that you just shuffle around, like let it go across machines, and every time you just do the same thing all over again. But this is not efficient at all. Why? Because the arrows here are still very vertical. It's still very localized. So then you can see that it's totally useless, not to use another word, to send over the data across machines. So it's better to do things like that, right? To basically let every initial value go through all the different transformation layers, but on the same machines. So this is an optimization that is actually done in practice, and that's called a stage, right? This is something you don't have in MapReduce because you don't have multiple maps, right? But in Spark, you can. who understand that if we have this pattern here with what we call narrow transformation, the localized one, we can group them in that way and execute very efficiently without shuffling. Okay, very good. So you see, this is called a stage, and it's a sequence of parallelizable transformations, narrow dependency transformations. So the narrow dependency means this, right? That you can actually split over multiple machines. And then this is just an updated screen. So basically in the preceding one, I only had one single transformation shown, but here we have two transformations shown. It's a series of two transformations, but I squeezed them together as a single stage, meaning that I execute in each task, I go all the way down the many transformations, but in the same task, okay? So this is really like merging the two transformations as if it were a single one with only one series of tasks that are shared for all these transformations. This is called a stage. Who visualizes a stage in their minds? Well, the visual is here, right? This is a stage with multiple transformations. There is a question. Let me see. There is the break.
There's a question. What happens if one of the transformation fails? Do we recompute or restore it from cache or something different?
So it depends on the level at which it fails, basically. It can be several reasons. It might be that it fails just locally. It's on one machine crashed, and you still have the data in there. Then you just recompute locally on your machine. It might be that you spilled the data to disk and it's just gone from memory, then you just take it again from disk, right? Reload it into memory. It can be in the worst case that you actually lost intermediate data, then you have to start everything all over again, right? So it's really very dependent on the way that things went wrong, basically. Did it answer your question? All right. You deserve the break, right? So let's take 15 minutes of break. It's 3:01. So I'll see you at 3:16 for the continuation of the lecture.